Welcome to this presentation of Ortac. Thank you for watching it. The goal of this presentation is to showcase Ortac, a runtime assertion checking tool for OCaml. This work is the result of an ongoing collaboration between two institutions. The LMF is the new laboratory on formal methods. It's focused on developing deductive verification tools and advancing formal methods in general. IDES is a company where we build open source software using OCaml, the OCaml programming language. Our software covers a wide range of applications, including developer tools, compiler contributions, distributed databases, and embedded systems. You might not know OCaml, so we'll start by trying to give you a sense of what it is and why it's a relevant language to apply formal methods to in the first place. So OCaml is a general-purpose programming language. It has first-class functions and immutability idioms. It also provides some imperative features such as effects or mutable types, arrays, etc. And it also has some object-oriented features, although it's a bit less idiomatic. It provides a strong type system, so programs are statically typed in a way that ensures important memory safety guarantees. So specifically, there is no null value, and the type system does not let you manipulate uninitialized values. So although this eliminates a whole class of bugs, not everything can be encoded in the type system, and ensuring the functional correctness still requires extra tools and methods. So before we go into such tools, let's have a word about the structure of OCaml programs. So they are typically organized into modules, which basically contains types and functions. Modules are made of two parts. Implementations contain the definitions of the types and functions, and this is where most of the code lies. Interfaces show the declarations of the contents of the module only. They form a strong abstraction barrier between the implementation and its user. So nothing that is not exposed in the interface is accessible from outside the module. So let's illustrate this on a short example we are going to use throughout the presentation. It's a module implemented a bounded integer set data structure using two integers. So it defines a type set, which consists in a record containing a size integer representing its size and a mask integer representing its contents. So more specifically, the ith bit of mask decides whether I is in the set or not. So note that mask is mutable, and we are indeed going to modify that structure in place. So it also defines a create functions, which takes an integer n and returns a fresh set of size n. Note that OCaml features type inference, so you don't need to annotate n with its type. Finally, the add function takes an integer I and a set s, and modifies s's mask to set its ith bit to 1, using OCaml's bitwise operations. The implementation is complete now, so we can set up an interface on top of this. You can see it on the right side. It contains the declaration of the typeset, but its details are not exposed and are abstracted away and not accessible anymore. It also contains the declaration of the two functions along with their type. So it's also possible to release a bit the abstraction by exposing the type if needed. So here we are using the private keyword, which means that you can read the record fields, but the type checker will not let you modify them or construct the value of this type. So now on to Gospel. So Gospel is a behavioral specification language for OCaml interfaces. The motivation for this project is that although the type system and the abstraction protect you from some kind of bugs, and that makes OCaml attractive for applications where safety is important, it's still not enough to ensure the functional correctness of programs. So Gospel is inspired by other similar languages such as Spark, ACSL for C, or GML for Java. It is tool agnostic, meaning that it makes no assumption on the use of the specification, so it can be used for deductive verification, but also runtime verification. Our goal is indeed to build a verification framework with a variety of tools using this language. So the language is still pretty young, and it hasn't reached general acceptance in the OCaml community yet. but the idea is to provide a language that you can use to annotate the interfaces of your programs with formal specifications that describe their behavior. The language features a number of usual constructs for specification languages, so you can add function contracts with preconditions and postconditions. You can specify their effects or add exceptional behaviors. You can also write type specifications, including models and type invariants. You can also write ghost declarations or logical declarations, which can be predicates and logic and functions, or axioms and lemmas. We're not going to dive into the details of this feature here, but you can check the documentations and tutorials of Gospels if you're interested. So let's see an example of Gospel specification for our previous set example. So here is the interface that we wrote earlier. You can still see our type and two functions. The first thing we could mention is about effects and mutability. We can add a first contract to add. So notice that the first line of the contract is a header that is here to let us name the arguments and return value in order to use them in the rest of the specification. So add can modify the mask field of its arguments. So we will add a modifies clause to say exactly that. Let's add a bit more information now and talk about size. So we want to handle sets of elements from 0 up to 31. So we need size to be between 0 and 32. We of course require the same property at the entry of create, and we make sure that the return set is indeed of size n, the argument. Finally, add also requires that I is within the size of BV, otherwise you cannot add I into BV. There's another invariant that we could add, which is that mask is positive and smaller than 2 to size. Indeed, the maximum value of mask is the integer with size 1s, which is 2 to size minus 1. We have added type invariants, but we haven't talked about membership at all yet. So we can do this by introducing a memlogical predicate, which takes an integer and a set and decide whether the integer is in the set by looking at the ith bit using logical operations. So with this predicate, we can finally complete the specification by saying that after create, no integer is present in the set. And after mem, if an element is in the set, then it is either the element that I just added or an element that was there in the old version of the set. So not the use of old, which is a gospel primitive that lets you talk about the expression in the pre-state of the function. So here we're talking about BV as it was before the function call. A final note on the specification. Unlike some other specification languages, such as GML, Gospel is not designed to be executable. So here everything looks executable, but I could have written this spec with no definition for mem or with no bounds in my quantifications. And the spec would still be perfectly valid for Gospel. So we can already see how this is going to be challenging for runtime assertion checking. So this work is indeed focused on runtime assertion checking. The goal of Ortac is to read OCaml interfaces and their Gospel annotations, identify the executable subset of these specifications, and produce OCaml code that checks them. So in the process, the parts that are not executable are simply ignored, so you can still partially check the correctness. And it only requires the interface of the module and never reads the implementation at all. So it's totally independent from the implementation you've chosen for your module, and it doesn't break the abstraction barrier. So a motivation behind Ortac is that although deductive verification brings you the best guarantees, it's also hard to do and maintain from a software engineering perspective. So we are aiming at providing a fully automated, unintrusive tool that helps writing tests and finding bugs in your programs, whether you want to prove it afterwards or not. A bit more details on the workflow using Ortac. So here, the 3 red boxes are provided by the developer in a scenario where a specified library, so let's take our set again, is used by some arbitrary client code. So Ortac will read the interface file of the library and produce an implementation file, setrac.ml. So this code contains all the checks derived from the specifications. It calls the original functions in set.ml and wraps them to verify the properties before and after the calls. So this new module has the exact same interface as the original set.mli, as it simply overrides some values with wrapped one. So we can just copy the interface file over. In order to make the verifications and have proper error reporting, the generated code depends on Ortac Runtime, which is a lightweight external library containing various helpers implementing the Gospel standard library or handling errors. So once we are done with the verification, with the generation, the client can now call the instrumented code instead of the original one. So again, since the interface is the same, this is not intrusive for the client at all, and switching the checks on or off is straightforward. I will now demonstrate this workflow on our set example. So here we are. On the right side, you can see my terminal. I'm inside a small project containing only the set module and some client code. On the left side is my text editor. So at the top, you can see the set.mli interface that we wrote earlier with a mem function that I added. And at the bottom is the client code. So what it does is it reads an integer n from the command line, creates a set with this size, and then adds all the elements from 0 up to n-1. It also checks that before adding an element, the element is not present in the set, and that after adding it, it is indeed in the set. So as I said, Ortac takes an interface file and produces an implementation file. So I can give it the set.mli file. It will read the specifications and write checks in the setrac.ml file. So the interface of that module is the same as the set module. So I can just copy that over and that would be it. I can now build a project using OCaml build system and execute the client and give it, will give it an obviously wrong input, so I can give it 40. And Ortac indeed detects that this breaks the precondition of the function create. So I will now give it a more valid input, like 20. And now it detects another issue in mem. So the postcondition of mem saying that mem basically realizes the logical mem predicate is broken. So let's have a look at what's going on. And indeed, I can see that I used the wrong function here, so I can fix it. And now I can build my project again and run the client. And now I have no more error showing up. And indeed, whenever no error is detected by Ortac in the specification, the original program is left unchanged. Its semantic is the same. So here the loop terminates correctly and the program terminates correctly. Hopefully you've seen that using Ortac is quite easy, but translating Gospel code actually isn't. So here are a few highlights on some features that make the translation an interesting problem. So first, Gospel's integers are mathematical integers, so we make sure Ortac implements them using a library that switches to GMP integers when necessary. So this means that Ortac can detect overflow errors in programs. As I showed at the beginning, you may write quantifications over unbounded domains, and we are indeed not going to execute that, but Gospel tries to detect bounded quantifications, for instance, over integers in an interval, or over values in a finite data structure, and it translates them correctly. Part of the translation also requires that we use equality functions when an equality is written in a spec, or deep copy function when we compute all values. But OCaml does not provide a safe way to do this. For instance, OCaml's polymorphic equality may not coincide with Gospel's logical definition of equality, or can even fail or not terminate on some input. So we use the type information to derive such monomorphic functions, and use them in the translation in a safe way. Gospel has a rich logical standard library with data structures such as sets, bags, sequences, or maps, etc. So Ortac's runtime contain implementation of this, but we also again have to generate monomorphic functions from type information. For instance, if you're trying to implement a set in an efficient way, you would need a total order of the elements. So we use the type information to derive that when possible. And finally, another issue raised by Gospel not being executable is that Gospel's logic is total. So that means that functions can always apply and always terminate without exceptions, but their result may be undefined. So, for instance, that means that 1 divided by 0 has a meaning in a specification, but you just don't know its value. However, when it comes to translating, Ortac detects such undefinedness and reports it to the user so they can fix the specification. So we are working on applying this technique to real-world use case, and we are using Ermin as a starting point. Ermin is a library developed at Tidus, which provides a Git-like database, so basically a graph of commits which contain snapshots of your data. The first and simplest application was a modular arithmetics library called Optint, which we used to model 32 or 64 bits integers independently of the architecture the code is running on. We also tested it on a graph traversal algorithm that exists in Ermin to browse the commit history. From the software engineering perspective, this required a bit more work and is not fully done automatically at the moment, because the original interface is a bit too advanced for Ortac to fully support it. But it's still possible to use the tool on very complex code by wrapping it into a simpler interface before applying Ortac until all the features are supported. And finally, a more advanced example we are still working on consists of an array, so list recently used cache. So the list recently used values are discarded first. And we want to make sure that the correct data is discarded and that no memory leaks occur. So Ortac is applicable in various settings. So we wrote a fuzzing plugin that lets you plug it to fuzzers like American Fuzzy Loop or AFL Fuzz. So the fuzzer is in charge of providing interesting input to exert the specification, and you don't need to write a client at all. It's also possible to use Ortac for monitoring only by logging the unexpected events and letting the program run. For instance, if you're in the context of a server, you don't want to stop the program on every violation. So a word on perspectives to finish. We are addressing two main challenges at the moment. On the handling of the hold primitive, so recall that hold lets you refer to the state of an expression in the pre-state of a function. The current approach is quite greedy and copies a large part of the memory whenever an hold is involved, meaning that deploying Ortac instrumented code in production is not reasonable for performance-critical programs yet. So we would like to provide a finer analysis to determine the smallest subset of the memory that actually needs to be copied in order to correctly compute a hold expression and provide a soundness proof of that optimization. Another challenge consists in supporting type models. So in our example, we exposed the set type to be able to mention its masks and size in the specification. But in fact, a more idiomatic way would be to hide the type completely, making it abstract, and it's no longer possible to see the size or mask at all now. So in order to specify this, we can use Gospel's type models, which let you introduce logical representation of this type. So here we could model our set using an integer size and a set of ints called contents. So note that contents is mutable. So integer refers to Gospel mathematical integers, while ints are OCaml's bounded integers. So size is indeed mathematical, while contents contains OCaml values, so ints. The first invariant remains the same, but now it refers to the model size instead of the record field size, which may not exist at all anymore. And the second invariant states that all the elements in contents are within 0 and size -1. The main challenge when translating such models is that they are logical representations of our type, but they are never implemented anywhere. In particular, if Ortac needs to maintain them during the execution of the program to test invariants or properties, it needs to figure out how this data was mutated by the function. So that could be either by a programmer input or by analyzing the specification further. So Ortac is still a young project, so there are plenty of interesting issues when improving its performance or expressiveness. Thanks for watching this presentation. Ortac is an open source project available in GitHub, so feel free to give it a try and contact us as we are always happy to hear feedback from users. Thank you.